Oh, that's weird. It's not really
Goes that way, I think. So yeah.
I'm sure. Yeah, it's opposite way around.
It goes that way.
Good evening, Year 11. Welcome to your Physics Paper 1 revision session with me, Mr. Nessie, Mr. Schuller and Mr. Catterall. So Mr. Catterall is going to go through the first couple of spec points with you, and then we'll have separates at 7 o'clock. Over to you, Mr. Catterall.
Okay, boys and girls. Right, okay, let's just have a quick look at what we're going to be doing in this evening. So it's fantastic physics on this terrific Tuesday, ready for our wonderful Wednesday's exam. So let's just remember that energy is our spec 1. Electricity is spec 2, and those were both taught to you in year 9. They went on to atomic structure and particle model through year 10. Now I'm going to focus initially on energy, and we're going to look at some key points throughout that. But first, let's remember our equations for tomorrow. Really important top tip here. As we go through these specifications, we're going to look at the equations that you need to know. But tomorrow in the Trilogy exam, you're going to get these equations to actually use within the exam. For separates, you get a few more equations, but let's just remember these are the equations that we're focusing on that you've got to be able to use tomorrow. And the first thing that we would like you to do when you get into that exam is turn over your equation sheet that you've got and write down as many of these as you can remember. Now, in tomorrow's exam, we are really looking at using these equations. But just remember, any of those equations can be used in any of those exam papers. So let's start looking at our first exam specification, and that is energy. So what's in the energy specification? That was the first thing that you did in year 9. So let's just reveal the first thing are our 8 energy stores. We then have our kinetic energy, particularly needing to know our kinetic energy equation. We've got gravitational potential energy, and these two, we're going to see in a little while, are really closely linked in some of the questions that they're going to ask you. We then have elastic potential energy. Big plus with this one, they give us the equation on our equation sheet. Specific heat capacity, we get the equation, but let's just remember that's one of our required practicals. We're then going to look at power and the power equations that we use, energy transfers, efficiency, and then finally the energy resources. Now, with energy, we actually do have quite a number of equations that we've got to use. So we're going to be asked quite a few of our mathematical answers. But let's get straight onto it. So I'm going to be using lots of questions through this evening's revision. So the first thing is you need to know what the 8 energy stores are. So if we actually think about those 8 energy stores, let's think about some of those equations that we've got to use. So we've got kinetic, we've got gravitational potential, we've got elastic. Then let's always think that when we get any energy transfer, we've got thermal. Okay. We've also got nuclear from the atom. We've been enjoying some food, so that links into chemical. Okay. Then there's two that we often don't think about, and they are magnetic and then electrostatic. Now, these 8 energy stores, they're the ones that you need to know about, and you need to be able to say how they transfer from energy is transferred from one store into the other. And there are 3 things that we need to remember about them. We have mechanically, and that's when we use a force or work is done. We have electrically, and then we have thermal or by heating. So when we actually get a transfer of energy from any of these to the next energy store, it's always going to be through one of those 3 methods, okay? So if you think about it, something's transferred because something mechanically is happening, so a force supplied or we're doing work, that we've got electricity involved, or there's something to do with heating. Let's use that as an example. So chemical energy, such as food, can be transferred into kinetic energy, which is movement, because of respiration from your biology, which is about the transfer using heating. Okay. Now, we've got 2 equations that we've got to know, and they're like linked together when we're talking about kinetic and gravitational potential energy. So if we think about the kinetic energy equation, so kinetic energy is about movement. So anything moving has kinetic energy. The faster it's moving, the more energy it's got. The slower it's moving, the less energy it's got. But we need to be able to work out kinetic energy. And because we know it's about movement, okay, the kinetic energy equation, so I'm going to put KE for kinetic energy, equals 0.5 multiplied by the mass of the object multiplied by velocity squared. Now, a couple of people have asked me over the last couple of days, well, does it have to be velocity or does it have to be speed? Velocity is the right word, but we do actually mean the speed of the object, okay? Now, we've got to remember that if we've got calculations around kinetic energy, think about our formula triangle and always think that the line represents the divide sign and everything with a multiplication like we've got here goes at the bottom. So 0.5, I'm just going to use the symbols times v squared, and kinetic energy is EK. Now, one of the questions I could ask you tomorrow is to actually calculate velocity or speed. Now, what I want you to remember is that when we rearrange this equation, v squared equals kinetic energy divided by 0.5 times by the mass. And if you notice, I'm using my maths conventions there, and I'm using my brackets because I would do this first. Now, if I had that number, multiply those together and divide the answer from that by that, I'm only ever working v squared out. So remember, to get our answer, we've got to square root that v squared, okay, to get v, okay? So it's really important. That's a missing trick that sometimes we actually forget when we're looking at that calculation. Now, when we actually look at gravitational potential energy is all about height, okay? So anything that's above ground, so this ball, for example, is above ground, it has got gravitational potential energy. When the ball is on the ground, okay, it's got no gravitational potential energy. So the higher you go, the more gravitational potential energy you have, okay? Now, because we know that gravitational potential energy is all to do with height, okay, it gives us a clue about how to work it out. Now we can see here that that ball has going to have some mass. So when we're calculating gravitational potential energy, we need to know the mass of the object. We multiply that by the gravitational field strength of wherever we are. Now, on planet Earth, we're always going to give you that in the exam, and it would either be 10 or 9.8. And we multiply it by the height at which it's moved to, okay? Now, I'm using these words movement and height because these two equations link together. And tomorrow, we could be a little bit sneaky and ask you to actually work out the gravitational potential energy of an object. So if I just use an example here. So let's say, for example, common question. There we've gone to Alton Towers. There's our roller coaster, okay? And I've got here Mr. Schuller and Miss Neresi, okay? They're on the roller coaster, okay? And they're going to come all the way down, all right? And as they come down, they're going, woo, okay? Because it's a long way and they're going to be going really fast. Now, I could actually say to you that the starting height, okay, is 3 meters, okay? That's 3 meters above ground, okay? The mass is 1,000 kilograms, okay? And the gravitational field strength of planet Earth is 9.8. Now, if I think about my equation, which is I want to work out the gravitational potential energy, so GPE equals mass 100. I said 100, yeah, 100 multiplied by 9.8 times by 3. And that would work out how much energy we've got up here. Now, remember, energy, gravitational potential energy, kinetic energy is always joules. Okay, so we've worked out this. Now, the sneaky question I could ask you is, well, if they've got, let's say, 250 joules of energy when they're here, okay, as they come down the hill, all right, what would be the kinetic energy that they would have when they reach the bottom? Now, this is where we've got to remember that rule that energy cannot be created or destroyed. It can only be transferred from one form into another. So in this case, I'm transferring gravitational potential energy into kinetic energy. So if I start off with 250 joules of gravitational potential energy, by the time I get to the bottom, okay, and Miss Neresi and Mr. Schuller have gone, woo, all the way down, they are going to have converted that gravitational potential energy to 250 joules of kinetic energy, because energy cannot be created or destroyed. It can just be changed from one form into another, okay? So this is where I have this little link, and it's like an exam question. If a ball has 100 joules of kinetic energy when thrown up, how much gravitational potential energy will it have at its highest point? Now, because it said highest point, we're looking at, okay, gravitational potential energy, okay? We're looking at an energy transfer. And do you know what? The simple answer is 100 joules. And top tip here, just remember, if you've asked you to do a calculation on kinetic energy or gravitational potential energy, and they ask you about either one, it's worth 1 mark, it's the same number, okay? And often we get confused by that. Now, elastic potential energy, okay, is one of our other stores. And what we're talking about here is when an object is deformed or not. So I'm going to take this pen here, and if I actually bend it, and it bends a little bit, and I let go, okay, it springs back to its original shape. So it's got elastic potential energy. And when we're actually calculating elastic potential energy, we're given on our equation sheet, okay, the equation for elastic potential energy. It's equation 2 on Trilogy, and it's equation 4 on separates, okay? So the key thing here is around about being able to actually calculate one or other of the component parts. So again, thinking about our formula triangle, Elastic potential energy, its symbol is EE, goes at the top. The rest of the numbers go at the bottom, okay? Spring constant, just put SP there, an extension, but extension is squared, okay? Now, let's just think about some of the units that we have here. Because it's energy, it's always going to be in joules, okay? Spring constant, well, let's come back to that. Let's think about energy, okay? Extension, that's going to be in meters. And our spring constant, all right, well, it's about applying a force. So that's going to be Newton meters, okay? So we've got our units, we've got our equation, okay? We can look at rearranging it. And now this comes back into a practical that you might have done around about Hooke's law. Now let's remember this, because they often ask you about this. You have a ruler, you have a spring, and then you add some masses to it, okay? Now, remember, we need to know our length of our spring at the start. It's 2 centimeters. We apply a force, and let's say that's 10 newtons, and the spring stretches. And its extension is the difference between its original length and the length it stretches to. That becomes the extension. Now, the same with when we looked at working out velocity. If I'm giving you this equation and I'm giving you some data and I need to work out the extension, remember using this equation, it's always extension squared. So when we're working out extension, we need to work out our answer as extension squared, and then we square root it, okay? Now, if we move on to the gram of a material, okay, to raise its temperature by 1 degree C, okay? Now, that is fundamental and really core there. So we need to know how much energy it takes for 1 kilogram of any material to rise by 1 degree C, okay? Now, this is one of your required practicals that you need to do. So you've done quite a lot of work on this. But remember, with any of these calculations, again, it's one that's given to you, but the actual symbols aren't very helpful. So always go to your word equation. So the change in energy equals the mass times the specific heat capacity times the temperature. Okay, and we've got our formula triangle. So just remember, when we're actually looking at this, we need to know the mass of the object. We need to know the temperature change. So we need to know the difference between the start and the finishing temperature. Okay. Now, if we're given specific heat capacity, it's straightforward. Multiply them all together, and that'll tell you the energy. If we're trying to work out the specific heat capacity, that's where we need to rearrange our formula, okay? So again, if I wanted to rearrange it to look at specific heat capacity, that would equal our energy, okay, divided by or over our mass times the temperature change, okay? So we do that part first, divide it by the energy, and that would give our specific heat capacity. Now remember, different materials have different specific heat capacities. So let's just go back and remind ourselves about that required practical that we need to actually think about, okay? So when we're doing our required practical, let's just remember we need to know the mass of the material, and that's why we use our balance, okay? So we get a range of temperatures. But we also need something to heat up our block. And that's where we use, I'm going to put H here for a heater. Now, a sneaky thing they could ask you, and it links into electricity, and this is where our units come together, they could ask you to say, well, what's the circuit that we would use to then be able to work out the energy transferred? So to complete that circuit, we would need our power pack, okay? And we would need to use an ammeter. Okay, so I'm going to put A there for an ammeter. So I need a lead that comes out to my power pack into my ammeter, and then a lead that comes from my ammeter onto my heater, and then from my heater back to my power pack. Therefore, I've got one loop. Now, I need to know the potential difference across my heater, and that's where I'd use a voltmeter. Okay, put a V there, and that would just be connected straight to my heater. Now, once I've got those two readings, I actually can use my equations, okay? And the equations that I would be using would be P equals V times I, because if I want to work out the energy, I need to work out the power. Got my reading here, voltmeter, and my reading off my ammeter. And then, for me to work out the energy, okay, that's transferred, I need to use power equals energy divided by time, sorry. Okay. Now, I've got my time, because I've got 1 minute, 2 minutes, 3 minutes, so I take my readings at those times as well. I can rearrange it. I've got my energy transferred. Now, just remember, another skill I could ask you, and it might actually be nothing to do with your required practical, but they could give you a graph of data, okay, that looks like this, all right? And they could say, okay, what's the specific heat capacity of that system? Remember, we need to work out the gradient. So take the gradient of the straight line, and the specific heat capacity, okay, is 1 divided by the gradient. Okay, now that's something that's quite new, and we've done that this afternoon in our required practical bits, but it's worth mentioning again for those of us who weren't able to make that. Okay, so we've talked a little bit there and linked into power. So what is power? So the rate of doing work. Okay, now what is power measured in? Okay, well, it is the watt. Okay, so 1 watt means 1 joule of energy transferred per second. Okay, and we've got 2 equations that we could use. Okay, and those are power equals energy transferred divided by time, P equals E divided by T, or power equals work done divided by time. Okay, and they're basically the same sort of thing. Now, you would use those equations if we're looking at energy, any question around energy. We would look at using power equals energy divided by time. Work done, obviously, the work done one. Just remember, though, that time is in seconds, both cases. Power is in watts, capital W, and energy and work done is always joules. And that's the bit that catches people out, particularly around work done, that work done is actually in joules. So think about the power of an object and it being transferred. That's what we're really getting at when we're looking at our power equations. And then think about efficiency. Efficiency is just about how good something is at transferring energy. So if you've got something that is really efficient, okay, it's going to transfer more of the energy into what you want it to do. So think about this. If you've got a fridge, okay, there's our fridge. The whole point of our fridge is to keep things cold, okay? Now, if I'm putting electricity or electrostatic energy into that, I want that energy to go into keeping things cold. So the more efficient it is, okay, the better the transfer of energy into keeping it cold, which will happen, okay? Now, when we're looking at working out efficiency, we've got to think about 2 things. We're looking at efficiency when we're talking about power, and we're talking about energy. Now, let's remember the unit here. Efficiency is always a percentage, okay? So when we're thinking about those equations, we need to actually think about working it out as a percentage. So if I'm told in the question that I've got in front of me, can you actually explain how efficient this is when we're talking about energy efficiency? So we're going efficiency equals the useful energy divided by the total energy in, okay? So that's basically the calculation I'm going to do. Now, because I know that my unit is a percentage, when I've done that, I need to multiply it by 100. Now, if you remember efficiency for energy, Well, it's exactly the same when we're talking about efficiency for power, and that is your useful power divided by your total power in. Work out your answer, times it by 100. And there you've got your efficiency. Now, just remember, the higher the efficiency, so if it's 90% efficient, okay, most of the energy is being transferred into the job the device is supposed to be doing. If it's got a lower percentage, let's say 20% efficient, that means 80% of the energy is wasted. And let's remember that most wasted energy is thermal. When you get any energy transfer, you're always going to get a waste in thermal energy. And that's a really good thing to remember. So if they ask a question, well, how could the energy be lost in this energy transfer? Think always thermal energy, okay? That's what we're actually getting rid of, okay? It's being lost, anything that's happening, okay? Now let's just think about the definition of both those. A non-renewable energy source is something that once it's been used, it can't be used again. Okay, so think about which ways can we actually generate electricity or use energy resources which are non-renewable. Once you've used it, that particular thing, it can't be used again. Which ones actually can be easily replaced? So when we're thinking about non-renewable, we're thinking about our fossil fuels. And when we're thinking about our fossil fuels, remember it's coal, oil, very important to say natural gas. And it's important that we say natural gas, because if you say gas, that could be any gas, the air around us. And then we've got nuclear. And we've got nuclear because they're made up of minerals. Okay, so we mine them. Once they've gone, they've gone. So once we've burnt coal, okay, we can't replace it. It's burnt, it's gone forever. It's going to take millions of years for it to be replaced. Same with oil, same with natural gas. With nuclear, it's never going to be replaced, okay, because we can't make any more. But when we're thinking about renewable ones, think about things that can be easily replaced. So, wind. Think about solar. Think about geothermal. Think about wave. Think about tidal. Okay? Think about biofuels. Okay? And when I'm talking about biofuels, that could include wood. Now, let's just think about that. If I burn a tree, I can't get that tree back, but I can grow some new ones to replace it. It's not going to take millions of years, so I can actually do that. But one of the things they might ask you about, what are the advantages and disadvantages of actually using these materials? Okay, so what's an advantage of using our renewable ones? Well, an advantage is that quite easily, they're not going to run out. We're going to be able to use them, okay, for a long time. And what's a disadvantage? Well, they're not always reliable. So think about it. Today is, in the UK, very, very sunny. Okay, well, that is where we are now. Okay, but is it always sunny? So some days there might not be enough sunlight to generate electricity. Is it always windy? It could be not enough wind, too much wind. Okay, geothermal, only good where you actually have those sources. Wave, okay, wave and tidal, yeah, if you actually have, you're an island like we are, really good. Biofuels, not a good advantage, takes a lot of land, okay? And then we've got, obviously, hydroelectric, okay? Again, takes a long time for your lakes to actually fill up. Now, a big disadvantage of all of these is cost, okay? A really good advantage of these ones, so a disadvantage is the cost. a really good advantage of these is that they do not produce any carbon dioxide, and that carbon dioxide then does not contribute to global warming. Okay, whereas let's think about our fossil fuels. Well, our fossil fuels are readily available. The power stations or using them are relatively cheap. Okay, big disadvantage, okay, particularly of these ones, is that they produce carbon dioxide or sulfur dioxide, and these contribute. Now, never, ever, ever, ever say pollution. We must name it. Okay, it's carbon dioxide, sulfur dioxide, and they contribute to global warming. You could even actually say, because they put particulates in the atmosphere, to global dimming. Nuclear, okay, lots of radioactivity. And that radioactivity is around for millions of years. So for nuclear power stations, super expensive to build, super expensive to decommission, to take down at the end of the lifetime. There's always a danger because of the radioactivity of the risk of contamination or a catastrophic disaster like Chernobyl or Fukushima. Okay. Now, okay, so we've actually gone through the main essence of energy. I'm just going to pop on here the energy, the equations to do with energy, and just highlight which ones that we'll be looking at you being able to remember for the energy topic here. As we go down, you can see there's quite a few of them that sit there within that energy topic. 1, 2, 3, 4, 5, 6 at least. Okay, we're going to have a quick 2-minute break. Is it not? All right. Okay, I'll do it really quick. I thought it was going quite quick. Should tell me. Okay, ladies and gentlemen, let's come back and go through electricity. Okay, right, let me just quickly go through what's in the electricity module. Circuit symbols, 14 of them. We're quickly going to look at those. We need to know what current, potential differences, charge, resistance, series and parallel circuits, electricity in the home, come back to power, and then the national grid. So I'm really conscious of time, so I'm going to go through some of the key essentials that you need to know for tomorrow's exam. Now, you're going to be asked to do some circuits in some guise, whether it's actually to draw a circuit, series of parallel circuit, or to identify a circuit symbol. So let's get started. The 14 circuit symbols that you must know. Let's start with the easy ones. Well, we've got a closed switch. We have, an open switch, an ammeter, a voltmeter, a bulb. Okay. Then let's think about a resistor. Now, when it's a rectangle, it's always a type of resistor. Our next one, a line going through it, is a fuse. We then have a variable resistor. We then have a thermistor. Okay. We then need to think about, okay, the resistor that's in a circle, which is our LDR. Okay. All right. We then go on to look at our diode. Now, remember with diodes, I'm just going to highlight here because it is very important. They can only go in a circuit in the correct way. The arrow, I'm going to color it in like that. That says the current will only flow in that direction only. So it only goes in one direction, your favorite boy band. And then we've got our, it's a diode again, but it's emitting light. So it's an LED. And then the last two, we've not done them, but they're very important. It is our cell and it is our battery. Oh, and I can hear you saying, no, but sir, you've not labeled it correctly. Remember the tall line, you must have a positive on there. Only put the positive on, you don't need a positive or a negative. And just remember, electricity, I'll use a blue pen, always goes that way around, okay, from positive to negative, okay? So, all right, we've got potential difference, we've got current, and we've got charge. So what is potential difference? Potential difference is measured in volts using a voltmeter, and it is the force that pushes current around the circuit. So without any potential difference, without your voltage, nothing is going to happen. Whereas current, okay, current, all right, carries charge, okay, and your charge is all about the transfer of energy, okay. So current, we talk about it being in amperes, okay, or amps, symbol A, and we use really handily an ammeter to measure it. Charge, okay, that is coulombs, capital C. Now that's the thing that we forget about. Now the charge transfers the energy, the current carries the charge, and the potential difference is the force that sends it around the circuit. So let's just think about these things, okay? Resistance. Resistance, okay, it's about reducing the flow of current, okay? So when something has got a high resistance, okay, we get less current flowing. Things with higher resistance are generally heat up, okay? And that's because you get the collision of the electrons with other particles, other parts like other electrons or atoms, okay? Remember your equation that you're going to use, V equals I times R, okay? So if you want to work out R, that would be equals V divided by I, okay? It's one of the equations that you've got to remember in there. But remember, something with a high resistance, okay, reduces the flow of current. Now, you're going to be potentially asked to recognize the IV characteristics of a number of devices. So here we have a resistor, and it's at a constant temperature, okay? And this follows Ohm's law, dead simple. It's just a nice straight line that goes through there. Directly proportional relationship. Whereas you've got a bulb, now a bulb, it heats up, and therefore resistance increases. and therefore you get a little S shape like that. And if you think about it, that S, if you put the line there going across it, it looks a little bit like a fancy fur. So it's an easy way of being able to remember that one. And then your diode, remember your distance, we use that to control lights. It's a common question they ask. But they might put the graph on around how does resistance affect when you've got dark to light, and the shape of your graph is like that. So your resistance reduces, okay, as your light increases. Here we've got a thermistor, and a thermistor is all to do with temperature. And we use those in thermostats, easy one to remember. And again, similar shape graph. As the temperature increases, okay, the resistance decreases. Okay, so let's just remember some of the rules around series circuits. I've drawn you a series circuit here. Okay, I've got a cell and two bulbs. So let's just remember the key things. That the potential difference in a series circuit is always shared. Okay, whereas the current is always the same. Now, if I wanted to actually put a voltmeter to represent the voltage in here, it must always go in parallel to the object, whereas my current, my ammeter, goes into the loop. Okay, and let's just remember here, if they ask you about the resistance, there's resistance 1, there's resistor 2, okay, they all add together. Okay, so that's the basics about your series and series circuits. Whereas when we look at a parallel circuit, the potential difference across all components is always the same, whereas the current is shared. Okay, so again, if I wanted to know what the potential difference is in the bulbs, I put my voltmeters like this. Okay, and very importantly for the current, because I've got two loops here, put your ammeter on the branch next to the component. So I put my ammeters like this. If I put my ammeter here, okay, I'm measuring the current in the whole circuit. So ammeters must go next to the device that you're going to do. Remember this though, with your resistance, it's always smaller than the resistance of the smallest resistor in the circuit. Just remember your electricity in the home. I know we're going really rather quick, but in the UK, potential difference is 230 volts and a frequency of 50 hertz. Okay, let's think about our 3-core cable. It's got a plastic outer. Each individual cable's got plastic. That's to act as insulation, okay, and reduce, okay, electrocution or loss of electricity. Then we've got our 3-pin plug here, cable grip, a fuse. A fuse is our safety device. We have our earth, okay, and then we have I have to remember a little thing from our top, blue to the left, going to the left, and that would be our neutral. This would be our live, okay? Now remember that the fuse only comes into operation when there's a difference between the neutral and the current in the live cable. Let's remember the colors, blue, brown, and then green and yellow up the middle, okay? Now, they might ask you a question about that plug to actually say, what do we mean by double insulation? That just means the cables are made out of plastic, the plug body is made out of plastic, therefore it reduces the chance of electrocution. National Grid, okay, coming towards the end now, really quite simple. All right, power station, the National Grid is nothing more than this section here, a step up transformer, a step down transformer, and then we've got the cables. Okay, that's the National Grid. Now, a step up transformer increases the potential difference or the voltage and reduces current. and it reduces the current, so it reduces, and this is very important, you say reduces energy loss, okay? Whereas a step-down transformer, that actually reduces the potential difference, okay, and increases current. And that's so it becomes useful for us to use in homes, okay? So we're just going to have a quick 2-minute break before Mr. Schuller carries on now with Spec 3. Was that quick enough then?
Right, okay, welcome back, Year 11. The next bit of this evening is taking you through Spec 3 and Spec 4. So all this is on particles and the particle model of matter, and also Spec 4, which is atomic structure. Now, the atomic structure stuff has got quite a few connections with chemistry, so it shouldn't be too bad. So we went through chemistry a couple of days ago, last week, sorry, and also you've done an exam on that, and you've also done some revision in lessons, so that should be fairly straightforward. Now, we seem to be down on views. We've got 63 people watching at the moment. There are not 63 people in Year 11. So get the message round, tell all your friends, tell your pals, and get people to tune in here, because we're not just sat here for the sake of it, and I need to see some more people coming in. If you've got any questions, we've got our Twitter handle is on this screen at the moment, and use a hashtag and it will come through. Mr. Nessie and Mr. Cattrall are sat by ready to take your questions and pass them on. Also, our Facebook page as well. If you search for Rising Community College Science Department, you can send us a message on there or post to our wall, and we'll answer them through there as well. Okay, so I'll take you through Spec 3. We'll stop, have a quick break, and then we'll go into Spec 4. So the first thing I want to look at with you is to do with density. Okay, density is about the amount of mass that something has in a given volume. Okay. Simplest way to explain it is by looking at the 3 states of matter, or the particle models. All right, so we're going to start off. We've got solid, liquid, and gas. Okay, now this is something that you will have done a little bit of work in primary school on. You will have done a little bit of work at Key Stage 3 on. You've covered it in chemistry, and you've also covered it in physics. So this should be nothing new to you. Key things to remember: 1, your particles must be equal size. Don't start chucking in little ones and big ones, because then you get into alloy territory, which is chemistry. For physics, we're looking for equal size circles. Don't make it hard for yourself and do these little tidgy things. Make them decent sized, okay? You've not got an infinite amount of time in the exam, so don't overcomplicate it. For a solid, we are looking for particles which are nice and neat and organised in neat rows, okay? They should all be touching. They should also touch the bottom of your box as well, okay? Don't have particles floating around. For liquid, we've got a little bit more of a messed up arrangement. Most of the particles will touch. The vast majority, you can have a couple of spaces knocking in. Okay, so you might have one or two odd little gaps in there. You'll notice now we've got more of a disorganized pattern. And you'll notice that the vast majority are also touching the bottom of the box. You don't have a cup of tea floating in your cup. A liquid will take the shape of its container. Okay, now you get the picture. I'm not going to make you watch me draw circles. That is a bit strange. Gas particles are the easiest and the ones that everybody gets right. Okay, gas particles are the ones that actually will spread out a little bit. They're not touching. They're as far apart as possible. Okay, so we're making sure in that one that we've got loads of space apart from the not touching. Now we're linking back to density. We're talking about the amount of mass something has in a given volume, or in simple terms, the number of particles around a given space. Looking at your three, this one, okay, has got the most particles in a given volume. So actually, typically solids have the highest density. Gases have the lowest density because they've got the least particles in a given space. Now, Miss Neresi just sent me a really passive-aggressive note saying to use colour. I was getting to some colour, Miss Neresi. I was doing the little bit first. So I do apologise, Year 11, if I don't use enough colour. Please let me know in the tweets if you'd like me to change colour or these aren't good enough for you. Miss Neresi is now falling out with me. Gas particles have got the lowest density. Okay, so dead simple. Solids highest density, gas is lowest density. Now, you could be asked how to work this out in the exam. For this, we're going to need an equation. You may see it as P equals M over V. P stands for density. I'll just get a different coloured pen. P equals density. Now, for you, we're looking at kilograms per metres cubed. Unless it may say on a rare occasion, put it in grams per centimetres cubed. But most of the time, you will stick to that one. Okay? We've got your mass, then in kilograms. And you've got your volume in, meters cubed. Okay, and just because it's a divide doesn't mean you can't magic triangle it. So by all means, you're pretty confident with those now. We've taught you consistently how to put things into your formula triangle. Okay, so you've got density, mass, and volume. So just like any other formula we give you, you can cover what you're looking for and you can do whatever you need to do. Okay. I want to go back to the particle model a little bit. I know I went off on one, but I want to go back to this now because there's a lot of information you can get from the particle model, and there are 6 markers that could come up on this. On the old specification, there were a number of 6-mark questions asking you to describe various features around the particle model. First thing I want to look at are changes of state. So what we call, we go from solid to liquid, liquid to gas, all that sort of stuff. Then look at the movement of particles, the energy the particles have got, and whether, when you go from solid to liquid or liquid to solid, whether you're gaining energy or losing energy. Okay, so we'll start off with the change of state. Solid to liquid is melting. When I teach this, I always talk about the example of ice to water to steam, just to keep it dead straightforward. I don't complicate it. We just look at something that way. Liquid to gas, we've got in our case evaporating, or you can use boiling. Gas to liquid, condensation. And then liquid to solid, we've got freezing. The little cheeky one that they will sometimes stick in is if you go from the solid all the way over to a gas, which is that one right at the top, and that is what we call sublimation. Okay, Classic example is iodine crystals. So you can get purple iodine crystals, you heat them up, they will skip being a liquid and they'll go from a solid straight into being a gas. Okay. Next thing to talk about is energy. When we are going, I'll just get a nice pen, when we're going from solid to liquid, we are gaining energy. Liquid to gas, we're gaining energy. Gas to liquid, we're losing energy. And then liquid to solid, we are also, and I'll squeeze this sort of in this bit, we're also losing energy, okay? So solid to liquid to gas, we're gaining. Gas to liquid to solid, we are losing energy. And so obviously this one, solid to they vibrate. Okay, don't talk about not moving, that is not true. For solids, they vibrate around a fixed point. So they're stuck there in one place and they are vibrating around. Liquid, they're able to move. So solid, you've got something like this and they vibrate like that. I'm trying to show it where to go. In a liquid, they're able to move around and this sort of thing. So still touching, but they can move. Whereas in a gas, they are moving freely and independent of each other. Okay. In terms of the forces, here we've got strong force between the particles, independent of each other. Okay. In terms of the forces, here we've got strong force between the particles. Here we've got weak forces between the particles. So you can see from something as simple as 3 particle diagrams, there is a lot of information you can collect from this diagram. Okay. Here we've got weak forces between the particles. So you can see from something as simple as 3 particle diagrams, there is a lot of information you can collect from this diagram, okay? So make sure that you read through this because it could, I'm not going to say for definite, not predicting, but it could potentially, and it has been in the past, a 6 marker to describe the properties around that. Something I could ask you is about what we call psi. Okay, our numbers have gone down. I'm taking it personal. We're down to 53 people. What is that all about? Don't forget, if you've got any questions, tweet us, use the hashtag AskTeamSci. Okay, our numbers have gone down. I'm taking it personal. We're down to 53 people. What is that all about? Spread the message. Pardon?
The brown pen.
Brown pen. It must be some. I haven't just used it though. That's sad. I'll change back. Oh, 54, 1 person listened. So we've got internal energy. 2 features make up internal energy. Okay. In that, we've got, spread the message. Pardon?
The brown pen.
Brown pen. It must be some. I haven't just used it though. That's sad. I'll change back. Oh, 54, 1 person listened. So we've got internal energy. 2 features make up internal energy. Okay. In that, we've got potential energy. So internal energy is the sum of all the energy in the particles. Potential energy is what is potential energy. So internal energy is the sum of all the energy in the particles. Potential energy is what is used to change state. So to change from solid to liquid to a gas, the potential energy will increase. And I'll explain this with the diagram in a moment. You've also got the kinetic energy store. If you use to change state. So to change from solid to liquid to a gas, the potential energy will increase. And I'll explain this with the diagram in a moment. You've also got the kinetic energy store. If you heat up a substance, the kinetic energy will increase. So the amount of energy the particles have got will increase. That in turn increases the temperature. These are directly related. In simple terms, the faster the particles are moving, the more kinetic energy they have got. Okay. Now, heat up a substance, the kinetic energy will increase. So the amount of energy the particles have got will increase. That in turn increases the temperature. These are directly related. In simple terms, the faster the particles are moving, the more kinetic energy they have got. Okay. Now, the reason we're explaining this and I'm talking through this with you is because you may get a graph that looks like this. Okay. You need to be able to identify whereabouts. The reason we're explaining this and I'm talking through this with you is because you may get a graph that looks like this. Okay. You need to be able to identify whereabouts on here we've got a state change and whereabouts the three states of matter are. Okay. Now what I'll do is I'll label it up and then I'll explain it in terms of here we've got a state change and whereabouts the three states of matter are. Okay. Now what I'll do is I'll label it up and then I'll explain it in terms of the energy stars we just talked about. Simple way to remember it. If the line is going up and you've got a positive gradient, you've got either a solid, a liquid, or a gas. Now I'm going to use an example of ice and water and steam. So I'm going to use those three to keep it straightforward. So here we've got a solid, we've got our ice. This bit along here, we've got melting. Then we've got liquid. The energy stars we just talked about. Simple way to remember it. If the line is going up and you've got a positive gradient, you've got either a solid, a liquid, or a gas. Now, I'm going to use an example of ice and water and steam. So I'm going to use those three to keep it straightforward. So here we've got a solid. We've got our ice. This bit along here, we've got melting. Then we've got liquid. Then we've got, we're going to put evaporating or boiling. And then we've got on the side bit there, gas. Now, this can be explained using this idea of internal energy. So if we've got something, if we've got the temperature going up, sorry, I'm not labelling my axes, not to Mr. Schuller, that's your temperature, that's your time. If the temperature is going up, that means the kinetic energy is increasing. The kinetic energy is increasing, that means the temperature is increasing. So we're heating up our ice. This point here, when the line is flat, you'll notice the temperature is not increasing. That is because here, the potential energy star is increasing. So if you're heating up ice, the heat energy is used for one of two things. This bit going up here, the heat energy is used to increase the kinetic energy of the particles and raise the temperature. When the line is flat, the heat energy is used to increase the potential energy of the ice, which then causes it to change state because the energy is being used to break the bonds between the particles. We're then into a liquid, so the kinetic energy star is increasing, so the heat being supplied now to the water is being used to heat it up, so the kinetic energy increasing, so the thermal energy goes up and the temperature increases. We then get this bit here, so instead now of that energy, as the potential energy now is increasing instead at this point. So the energy being supplied to the water is now being used to break the bonds between the liquid particles, so the particles can evaporate, and we're now producing a gas. And at this point here, the kinetic energy star is increasing. Okay, so for example, water will turn into a gas at 100 degrees, but steam can get hotter than 100 degrees. That's why steam is a lot more dangerous than water, because it's got a hotter temperature and it's more likely to burn you. Okay, just one other thing as well as the shape of that graph, you need to be able to recognize it the other way around. So you've got gas, condensation, liquid, freezing, solid. So I'll go the other way around that way. So you've got gas, condensation, liquid, and a solid there. So it's basically just the opposite way around. So if you can't remember it, draw it that way, flip it around in your head, you're good to go. Okay, it's just literally spotting the pattern between them. Only the energy stars are decreasing. Next bit. Now, this bit I'm going to show because Mr. Cattrall has looked at specific heat capacity with you in Spec 1. I will say there isn't the required practical for it in this topic, but you do need to be aware of it. So know the equation, just like Sir talked about, know how to apply it, and know how to link it to your required practical. Okay? I will, like I said, I won't go over that because you have already covered it. I will pick back up then this topic at something called latent heat. Now, latent heat and specific heat capacity are a little bit confusing because they sound similar, okay, and they've got similar definitions. For latent heat, this is the amount of energy needed to change the state of 1 kilogram of a substance. So, for example, chocolate has got a specific latent heat, and that is the amount of energy needed to melt a kilogram of chocolate. The amount of energy needed to melt a kilogram of ice is its latent heat. And each material has its own specific value. So just like specific heat capacity, each material has its own value. It does for this. And the beauty of this equation, just like specific heat capacity, is you are given this little gem on your equation sheet. So you may see something like that. Okay. So energy required, E for energy. So this is the energy required. So you may see something like that. Okay. So energy required, E for energy. So this is the energy required. And all energies are measured in joules. Make sure it's a capital, as you will not get the mark. This is your mass of your material or your substance, which is in kilograms. And then you've got your latent. That's and all energies are measured in joules. Make sure it's a capital, as you will not get the mark. This is your mass of your material or your substance, which is in kilograms. And then you've got your latent. That's as latent. That's better. Latent heat, which is in joules per kilogram. Can't remember the units. Chuck those together. That's what mashes in to make your latent heat. Like every formula we use, you can magic triangle it. Okay, the two things that you multiply is latent. That's better. Latent heat, which is in joules per kilogram. Can't remember the units. Chuck those together. That's what mashes in to make your latent heat. Like every formula we use, you can magic triangle it. Okay, the two things that you multiply go at the bottom, and then the energy goes at the top. So if you ask to calculate the latent heat, cover up L, energy divided by mass. Now, what they will try and do is throw you off track a little bit with this year 11. They may use 2 go at the bottom, and then the energy goes at the top. So if you ask to calculate the latent heat, cover up L, energy divided by mass. Now, what they will try and do is throw you off track a little bit with this year 11. They may use 2 particular terms. They might not just say latent heat. They may talk about specific latent heat, about something called, and I'm going to write these on so you can refer to them later. That makes sense. Specific latent heat, first of all, of fusion, which is a specific latent amount of energy needed to melt a kilogram of a material. Okay, so melt 1 kilogram. You've also got the specific latent heat, squeaky voice, it's been a long day. I've missed out heat out of that one, sorry everyone, of vaporization. And there's a little bit of a clue here, okay, because it's the amount of energy needed to turn a kilogram of material from a liquid to a gas, so to evaporate or boil. So vaporization, you're turning something into vapor, so a kilogram of material from a liquid to a gas. Have we had any questions through, Miss Neresi?
Just asking if there's intervention in the morning for physics. There's no intervention.
I'll be available in the morning in the heart space. I'm not teaching all morning, so I'm literally going to sit myself in the cafe bit of the canteen. Just turn up. If you want to do some revision, brilliant. If not, that's fine. My classroom's open as well. It's free, so I'm just going to literally do a bit of an open surgery. So if you come with any panics, anything you're not sure about, call in, come and find me. I'm available in the morning from, if you're sad enough to get in at 6:30, from 6:30 up till 9:30 to when you start. So if you've not got the exam in the morning, which is business, I think you do this exam in the morning, more than welcome to offer you some assistance, okay? But don't just turn up and say, I don't get physics. Please come with specific questions, bring your revision guide with you, bring your notes with you, and I can go through it. If you just come and say, can you teach me about physics? The answer will be no. I'm only going to answer specific questions for you. Okay, so that is topic number 3. We're not going for a break purely because we are conscious of time a little bit and we are overrunning a little bit. Now, this is touching on now spec 4, which is what we call atomic structure. A lot of atomic structure is what we call common content with chemistry. So I am going to talk about James Chadwick because we all spotted the question on the chemistry exam, if you got that one about James Chadwick, and you were a little bit, oh, James Chadwick, who's he? So we'll cover him tonight just to put your mind at rest, just to make sure you know who he is and what he did. The first thing to remember is the structure of an atom. Okay, chemistry knowledge, key stage 3 knowledge, you should know what this is. If you don't, please watch this back and make sure you know what you're on about. Nucleus. Inside the nucleus, positive protons and also neutral neutrons. Sorry, orange pen's a bit dead. We've also got around the outside things called shells, or in this topic you may hear them referred to as energy levels. And on those energy levels you will find your negative electrons, which sometimes we draw, and I put that as a negative so you don't forget, but sometimes we draw them as a cross. So you may say that, or a little bit of chemistry, you may draw them as a dot, you've got dot and cross diagrams, okay? Couple of facts here. Foundation paper, I've seen them as multiple choice in the past, but it could also appear on a higher paper. You need to know some key figures for this one. The radius of an atom.
That's brand new, so that they need to know that under 1 mark.
Okay, so the radius of an atom is 1 times 10 to the minus 10 meters. Okay, you can leave it in standard form. You don't need to start chucking loads of decimals and zeros and things all over the shop. You can leave it as that. That is a key point you need to remember. Also, you need to know that the radius of a nucleus is very small compared to the radius of an atom. All right, so the radius of the nucleus, and I'm just writing this down word for word, is 1/10,000th the radius of an atom. Two key facts to remember for that one. Oh, we've gone up to 50 people. I must have said something good. So the radius of the nucleus, so the radius of that bit, okay, is 1/10,000th of the radius of an entire atom. So we're talking things that are well smaller here, okay? So remember them key figures. One thing that Will could chuck in there is about the absorption and emission of energy. When we talk about alpha, beta, and gamma, we talk about atoms absorbing the energy or absorbing the radiation. If an atom absorbs energy, and there's certain terminology you need to use here, so make sure you're very specific with your language. When an atom absorbs energy, the electrons are promoted to a higher energy level. In simple terms, I'm just going to put NRG, shorten it down a little bit. This means that they move away from the nucleus. If an atom emits energy, so gives energy off, what pen is red one? So if it emits energy, electrons, you could say, demoted to a lower energy level. Okay, so I'll write that down here so you can watch it back. Sorry, moving the sheet, getting excited. Sorry, I can't multitask. This means that the electrons are moving towards the nucleus.
Got a question, Mr.
Oh, lovely,
Schiller.
because we've got 38 people watching, so any conversation will be greatly
from
appreciated.
Ali in 11E1. Is the radius of the atom the same for all atoms, regardless of number of shells?
Yes, the radius of the atom will be exactly the same. So that is, for any question, that is a key definition you can just bang out. If you get a 1 marker,
That's the only thing they need to be able to regurgitate.
Yep.
Keep at it.
it's just something you can just knock out straight away. For the process of this question and for this topic, that is one number that will not change. It is 1 times 10 to the minus 10. Okay, good question. Thank you, miss. So atoms absorb energy, the electrons move away from the nucleus. If it emits energy, they move towards it. Okay. Couple of definitions. Bit of cheeky chemistry once again. Isotope is when an atom has a different number of neutral neutrons. Now, when we talk about radiation later and radioactive nuclei or a radioactive nucleus, they usually come from unstable isotopes. So when an atom has a different number of neutral neutrons. For example, a common one, carbon on the periodic table would look like this. Now, I'm not going to recap how to work out protons, neutrons, electrons. You should do, no doubt, to do that. You have recapped that multiple times. That top number, okay, tells you protons and neutrons. If we work it out, it's got 6 neutral neutrons. There is an isotope of carbon that looks like this. Now, I'm not going to recap how to work out protons, neutrons, electrons. You should do, no doubt, to do that. You have recapped that multiple times. That top number, okay, tells you protons and neutrons. If we work it out, it's got 6 neutral neutrons. There is an isotope of carbon that looks like that. Okay, it has got 8 neutral neutrons. It has got like that. Okay, it has got 8 neutral neutrons. It has got 2 extra. Okay, that's all it means. So you, particularly this one, this is a radioactive isotope that is unstable. And that's when we start looking at alpha, beta, and gamma, where this bit fits in. So we'll come back to that later. 2 extra. Okay, that's all it means. So you, particularly this one, this is a radioactive isotope that is unstable. And that's when we start looking at alpha, beta, and gamma, where this bit fits in. So we'll come back to that later. Ion, dead simple, different number of negative electrons. So I'm not going to bore you with ionic bonding. You can recount yourself, as long as you know that if you gain or lose negative, Ion, dead simple, different number of negative electrons. So I'm not going to bore you with ionic bonding. You can recount yourself, as long as you know that if you gain or lose negative electrons. If you change the number of protons, okay, you get a different atom. So if you've got, for example, carbon's got 6 protons, chuck another one in there, it becomes nitrogen, another one becomes oxygen, another one becomes fluorine, and so on. So all of a sudden, if we start changing electrons, if you change the number of protons, okay, you get a different atom. So if you've got, for example, carbon's got 6 protons, chuck another one in there, it becomes nitrogen, another one becomes oxygen, another one becomes fluorine, and so on. So all of a sudden, if we start changing, I'm just going to put different positive protons. Okay, so make sure that you just chuck just a little bit of background information, that you chuck that in there as well. Okay, now history of the atom. Keeping it simple, keeping it brief, conscious of time, you've done this already. However, I know there was a little bit of outcry from multiple people about particularly James Chadwick. Everyone forgot about listing up poor old James Chadwick. We focus on other stuff. Okay, you do need to know the bigger picture. I'll draw this with some pictures. I'm going to stick to black for this one, just to keep it simple. Sorry, Mr. Ressitt, because I'm spending more time picking pens at the minute. The very beginning of the story, atoms were believed to be solid spheres that could not be broken down, look at its beautiful colouring into anything smaller. That is the start of our story. Mr. Ressitt showing no disapproval of my colouring in. Then someone called J.J. Thomson came along. J.J. Thomson did some work around atoms, and he proposed something called the plum pudding. And his idea was that an atom is a sphere of positive charge, okay? And in that sphere of positive charge, there are negative electrons randomly dotted about. There's no pattern to it. In those days, it would be like Christmas pudding or Christmas cake. You just get random raisins chucked in all over the place. This is the same. There's no pattern to it. Brilliant. Then a little bit of time later on, a gentleman called Ernest Rutherford came along. And Ernest Rutherford did some more work. Now, this is something that I will come back to afterwards, because we need to explain a bit more work around what Rutherford said. He proposed something called a nuclear model, okay? So he was a gentleman that said, actually, in the centre of your atom, there is a bit we call the nucleus with all the positive protons in them, and the negative electrons are around the outside, scattered around. Okay. The next gentleman is our best friend, Niels Bohr. He said, okay, Ernest Rutherford, I see your model and I'm going to raise you one extra thing. He actually said, brilliant, but as well as the nucleus in the middle with all the positive charging, the electrons are not just chucked all over the place around the outside. They're actually on what we call shells or energy levels. Which, like that. And those electrons on the shells or energy levels orbit the nucleus. So you can see now we've gone from a blob to actually something that represents what we teach you today, which is what we call the, which is what we're called the nuclear model. Then it is actually now our proper best friend, Mr. James Chadwick, the one that we all forgot about. Okay, and James Chadwick, Chadders we'll call him. He said, actually, brilliant. I see what you're saying. Lovely. Thanks, Ernest Woodley. Thanks, JJ Thompson. There's a little bit more. I'm just going to put Niels Barmis's name off there. Sad. And James Chadwick said, actually, do you know what? Everything you said isn't wrong. I definitely agree with it. But as well as that in your nucleus, as well as a positive proton, we've also got some neutrons. So once again, we're building up that picture, okay? I like teaching this because it follows a pattern. It's nice. It just follows a nice, easy story. Now, I've been a bit overexcited and my atom doesn't fit on, which is useful on there, and then your negative electrons around the outside. And that is currently the atomic model that we teach you in lessons today when you do about chemistry. So we've gone from blob, plum pudding, nuclear model, electrons on shells, neutrons in the middle. Now, one thing that you could be asked about, and to be honest with the main bit, and the main bit of work you need to know about is this bit here, between MC Thompson and MC Rutherford. Those are the key bits, and this is the gold foil thing. Now, I am going to recap this. I know you've covered it, but this is really, really important, okay? I know we're overrunning, but please stick with us, and if you have got any questions, by all means, send us a tweet. Hashtag AskTeamSci. Mr. S is sat bored looking at a computer, looking at memes because there's no comments coming through. Facebook is open. If you search for Horizon Community College Science Department, we should come up at the top. Look for our school logo. Send us a message, slip into our DMs, send us something through, or post to our wall. Either or will come through, okay? But we are still getting some shocking views here. I know some people watch afterwards, but please spread the message around. This is the best way that we can give you some help at this late stage. All right? So, Ernest Rutherford, he did something called the gold foil experiment. In simple terms, he had a piece of gold tin foil, as you do. Because obviously aluminium foil is not good enough for Mr. Rutherford. Now, in this gold foil, obviously, there's going to be atoms. For now, I'm just going to draw this, and it'll make sense. Draw something that looks like a target. So a pair of boggly eyes. Now it looks like a three-eyed cyclops. And he fired alpha particles, and I'm going to use for this, I'm going to use that, the Greek symbol for alpha. I'll come on to this in a minute. He fired them. And there were three things I noticed. Three things happened. He spent ages doing this. It wasn't just something he did overnight or just sat over the weekend. This took months and months and months of him and his two understudies sitting in a dark room looking for this experiment to work. It was a big, long job, pretty boring, but it made something really important. Some of the atoms, some of the alpha particles went straight through. So this provided evidence that most of an atom is empty space. If J.J. Thompson's model was right, and that ball, that sphere is entirely made of positive charge, the alpha particle would get close to it, and because this is also positively charged, and so is that theory in the atom, it would be deflected. It would bounce back, but it didn't, went straight through. Scenario number two. Some of the alpha particles, let me just draw another one of those little bad boys there. I like little fish. I'm not going to put eyes on them because I won't confuse you. I'm resisting temptation. Some of the alpha particles travelled along and they were deflected. And that's a key word there. You must use that word deflected. And then this gave the conclusion that the nucleus is positively charged, and it must be where the protons are located. So because the alpha particle is positive and the nucleus is positive, two like charges will repel. So travelled along, and they were deflected. And that's a key word there. You must use that word deflected. And then this gave the conclusion that the nucleus is positively charged, and it must be where the protons are located. So because the alpha particle is positive And when it got close to the nucleus, it was deflected or repelled. And you notice the key words there that I'm using. I'm not using sloppy language. I'm being very specific with the words and the terminology. You need to do the same if there's a 6 marker on this one, year 11. There's one final thing that could have happened that links to this explanation. Okay. And instead of it being nucleus is positive, 2 like charges will repel. So when it got close to the nucleus, it was deflected or repelled. And you notice the key words there that I'm using. I'm not using sloppy language. I'm being very specific with the words and the terminology. You need to do the same if there's a 6 marker on this one, year 11. There's one final thing that could have happened that links to this explanation. Okay. Deflected. Actually, let me just use a pen. Some of the alpha particles headed directly towards the nucleus, and watch where this arrow goes. It has not touched the nucleus. It did not hit it. It did not directly knock into it. It did not bash into it. It got close. And instead of it being deflected, actually, let me just use a pen. Some of the alpha particles headed directly towards the nucleus, and watch where this arrow goes. It has not touched the nucleus. It did not hit it. It did not directly knock into it. It did not bash into it. It got close and it was deflected. It bounced back. It was repelled backwards. And it was deflected. It bounced back. It was repelled backwards. Do not say it hit the nucleus. Look, that one hasn't hit the nucleus and neither has that one. And any diagrams you get in the exam will also replicate this as well. So please be very careful, because if you put it hits the nucleus, you've lost a mark. You will not gain it. So we do not say it hit the nucleus. Look, that one hasn't hit the nucleus and neither has that one. And any diagrams you get in the exam will also replicate this as well. So please be very careful, because if you put it hits the nucleus, you've lost a mark. You will not gain it. So this was, and I want to put here, deflected, bounces back, repels. Okay. You may see it in the exam called something called Rutherford's. This was, and I want to put here, deflected, bounces back, repels. Okay. You may see it in the exam called something called Rutherford's scattering experiment. But if I'm honest, you probably get that in your blurb, but just to show you, so it's not, you don't panic and think, well, it was this bloke Rutherford. It's the same gent that we're talking about. Okay, so recap: posh tinfoil made out of gold, alpha particles firing at them, one of 3 things: straight through, deflected, bounce back. This is how Rutherford helped this idea move from this to this. Okay, through this. So make sure you look over that, make sure you recap it. So the bit that's the main sort of bit of this topic. We've only got a couple of bits left to do, and then what we're going to do is we'll pause for some questions, we'll have a bit of a break, and then it'll be back to Mr. Castro for separate revision set 1 only. But I'll let you know when that is. So Trilogy people, you can switch off, and then after the video's finished, we'll take it off, it will upload, and you can pause, rewind to your heart's content. Okay. So, 3 types of radiation. I'm going to black again for this because I'm going to draw a table. There's 3 types of ionizing radiation that you need to know about. There's alpha, there's beta, and there's alpha, there's beta, and there's gamma. Now, I'm going to include the Greek symbols here because they may chuck them in there for good measure. They may try and throw you off track. We've noticed AQA is a little bit cheeky at times. So just to cover our backs, that little fish thing I drew on the last one is the Greek symbol for alpha, beta, and I always forget which one we do.
Fish in its head.
That's the one. This is where I lose my spatial awareness a little bit. Why have I been so stupid? I'm going to turn it this way. That way, there's gamma. Now, I'm going to include the Greek symbols here because they may chuck them in there for good measure. They may try and throw you off track. We've noticed AQA is a little bit cheeky at times. So just to cover our backs, that little fish thing I drew on the last one is the Greek symbol for alpha, beta, and I always forget which one to do it.
Fishing its head.
That's the one. This is where I lose my spatial awareness a little bit. Why have I been so stupid? I'm going to turn it this way. That way, there we go. Something like that. Okay.
Fish pointing down.
Cheers, thank you very much, Mr. Cattrall. You helped me out there in a tricky situation. So you need to know what it is. You need to know a symbol. So I'm going to draw the table. Now, hopefully I can fit it all on if my fat handwriting doesn't take up all the space. So first of all, you need to know what it is. Alpha particles are we call a helium nucleus. It's made up of 2 positive protons and 2 neutral neutrons. Okay, and you can see, hopefully you can spot why the name comes from there. So it's finding a nucleus of a helium atom. A beta particle is a fast moving electron. Ping, 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 off you go. Gamma is a high energy wave. Now, when we talk about decay equations and stuff like that, there isn't anything involved with particles, no decay equation with that, because no particles involved, you won't get a decay equation for a bit of gamma. Okay, so a couple of things. Distance in air. You don't need a quantitative value, you just need to know whether it's low, far, not very far, a little bit, if I'm honest with you. Low, I'm going to put low, high, and then obviously that's just in between, that's medium. So alpha particles don't travel far in air, whereas gamma waves travel quite long distances. What is it stopped by? Alpha's stopped by paper. If we had a nuclear war and only alpha radiation was being emitted from whatever was exploding, you could make yourself a nuclear shower out of paper and you would be fine, okay? In respect to that also, alpha particles do not pass through the skin, so to be fair, you'd be okay. Beta particles are stopped by thin foil. And you don't have to be as posh as any other thing. You don't have to crack out your gold tin foil. Just thin metal foil will be perfectly fine. Gamma, thick concrete or lead. So any nuclear bunkers, particularly those meant for world leaders, dictators, presidents, anything like that, are made out of thick lead or concrete because they will prevent the people inside it being exposed to alpha or beta or gamma. Okay, so if alpha is stopped by paper, it is definitely been stopped by thick concrete or lead. In terms of, you might hear it called penetrating power, and everyone giggles because of the word penetrating. That one's low, that one is high. Okay, you may see a diagram. So that is paper, that is metal, that is lead or concrete, and you've got your alpha. Sorry, you need to know something called ionizing power. Now, we've talked about ions. Ions are when atoms gain or lose the number of. In fact, that when the radiation affects your body, it turns atoms into ions. That is then what leads to the nucleus being altered and the DNA being altered, which then leads to your mutations. Okay, so you can link your biology knowledge in here. You have talked about mutations and benign and malignant tumors. This is where it comes from, and this is the core reason why radiation is dangerous, because of the fact that it will turn atoms into ions, and then that links into altering the DNA in the nucleus, which causes mutations. Okay, high. You don't need a full chapter and verse, medium and low. Other way around, it's a long night. Let me try again. Help if I know what I'm talking about. Alpha is high, we'll try again. Okay, beta's medium, gamma is low. So a bit of a comparison here. So whilst alpha is only stopped by paper, it's got the highest ionizing ability. So if you were stood next to someone and they have sort of radioactive source and they're pointing alpha at you, you'd be okay. However, if you've got alpha radiation in your body, it would do the most damage. Whereas gamma, because that it can pass through skin, if someone was firing gamma rays at you, it would pass through your body, it would pass through into your body and back out, but it's got the lowest ionizing power. So if you ever get given a comparison, there's a number of things to consider with that one. Uses, just really quick, a couple of uses on. Alpha's used in smoke detectors. It chucks out a beam of alpha particles. Detectors, that is not a word. I'm getting overexcited. Smoke detectors. Beta is used in measuring the thickness of metal sheets. And gamma is used for mostly sterilizing. Video, you know where it is. You must look over that one. And if you've got any questions, by all means, get in touch. I'm going to ask, can I move it on? None of you can reply back, so I'm moving it. Last bit then, okay? I know we're going on. There's a couple of bits left. What time? We're about 1:30. Thank you for bearing with us, Jill. And we have got hardcore fans of at least 40 people, so we have got some people who like us. You may be asked to look at some a word. This one. Don't be scared. It's not a scary word. You have learnt about this, but you may not have called it transmutation. In simple terms, it basically means we have an unstable nucleus, it becomes stable, and it gives something off. It emits something in order to do that. That is what transmutation is. So, for example, you might have something such as, in our case, you could have radon, and you might end up with something like that. It's unstable, it becomes stable again, and it might turn into, for example, polonium, and it might give off, in our case, an alpha particle. Okay? So that's all we're talking about. So you've got radon, turns to polonium, emits an alpha particle. That is transmutation. However, drawing that little beauty in the exam will not pick you up many marks, if any at all. We need to use a way of representing it. And this is where decay equations kick in. Now, this is not a chemistry exam. You don't need to memorize the atomic number of radium. You don't need to memorize the atomic number of polonium or helium, anything like that. You are expected, in a way, just to balance numbers. So let me give you an example. Let's say we've got our unstable nucleus, which is at the top. So we've got our radium. We've then got what it's decayed into. Unstable nucleus, stable nucleus, which in our case is going to be our polonium. And we've emitted an alpha particle. Now, in this part of the topic, they will not use the funny little symbol there. It will always be 42He, always, okay? So don't start drawing sideways fish and all that stuff. No, it's this. If you see this, you know it is something that has emitted alpha radiation. You will be asked, potentially, you could be given this, and they could say to you, what type of decay is this showing? Is it alpha or beta? Now, for these equations, just like in chemistry, the numbers have to balance on both sides. What does that mean for you? Well, it means if you've got 219 there, these two numbers must add together to equal 219. If you've got 86 there, these two numbers here must equal, when you add them together, 86. A couple of cheeky ways of looking at this. If the top number changes, it's going to be alpha. Dead simple. Bare minimum. Top number changes, you've got alpha. If the top number, no change, that's broken English, is beta. So you can, if all else fails and you've got no idea what I'm talking about, you panic, you come to me in the morning, you think the world's going to end. It is not. Don't stress. Just remember, if the top number changes, you're on alpha, 42He. If it doesn't, we're looking at beta. Okay? You could be, like I said, asked to work out what it is, or you could be given a blank. So you might not be given that number, or you might not be given those numbers, and you could be asked to fill in the blanks and balance the decay equation. Add them up, it gives you that. Add them up, it gives you that one. Okay, so you're just spotting a pattern with that one. Don't overcomplicate it. Don't stress. You're just looking for patterns and you're balancing the numbers. Beta's got a story. Beta has a story. It's exciting. Here's what happens. In beta decay, a neutron from a nucleus is converted into two things. In our case, I'm going to draw two here. One there. First of all, it gets converted into a positive proton that the atom keeps, and a negative electron that the atom will emit. Okay? So your neutron's converted to the proton and an electron. The atom will keep the proton, which is why in beta, when I show you the atomic number, the proton number goes up by 1 to represent that, and the electron is given off. So when I said a beta particle is a fast-moving electron, it's this little bad boy. For one, more than one, is a nuclei. So please, once again, it's all about your language of this one, folks. You've got to be careful what you're saying, else they will diddly out marks if they can. They're not looking to give you sympathy marks and stuff like that. You've got to be clear. So, unstable nucleus. That's what we started with. That's what we've decayed into. So we start off with carbon, atom, neutron, electron given away, proton, which is why that bottom number, the atomic number, has increased by 1. To show what a beta particle is, we use 0. And people always think I've drawn an eye when I do this. 0, minus, 1, and an E. Okay, so whilst that's your alpha particle, this is your beta particle. That brown pen, I don't like it. That's your beta. And as you'll notice, you don't even have to play with the top number here. 14 plus 0 makes 14. Job's a good one. 7 subtract 1 equals 6. You're sorted. So same thing again, you could be asked to balance it. You could be asked to work out what type of decay it is. And if you remember our pattern, top number hasn't changed, so it's going to be beta. All right? So just make sure no matter what isotopes you've got, no matter what unstable nuclei you've got, it is the same process. Have you got any more card? I've run out. Oh, I've used the one that stuck to the table. Sorry about that, everyone. Okay, normal for gamma, because don't forget gamma is just a wave of energy. Now we're on to the last bit with this one. I apologise. We have overrun, I say a little bit, actually ridiculous amounts. We have overrun quite a lot, but we've got a stable number of 62 people, so I'm guessing that people are digging what we're doing. Question?
Question, the last bit that you did, is this higher tier or?
No.
No. Okay.
Everything that myself I've done in topics 3 and 4, all of it is foundation and higher tier. There is one bit that is going to be higher tier in a minute, and I will tell you what that is. And Miss Cattrall's just confirmed that spec 1 and 2 was also foundation and higher tier. Okay, so even though it looks a bit panicky, you could be asked to do it. Okay, so please go over that. So half-life, I like this bit. This is a nice question if you get this, because actually once you learn the skill, you can apply it to multiple scenarios. Half-life, the time taken for the number of radioactive nuclei, or the time taken for the sample, the amount of radioactive sample, or the count rate, whatever it is, to fall to half. Bit of a clue here. Half-life, half of its original value. So please look for the clue in that one. Don't panic yourself. 2 ways I could give you some information on this one. They could give you some information as a graph. Where they could give you the activity in becquerels. They could give it you in count rate. Okay. They could give it you in mass of sample. They could give you in anything like that. It could be anything like that, but it will be the same pattern. Okay. So it's activity and it's time. Now, please be careful of the time unit. Seconds, hours, minutes, years. Anything like that. But whatever you quote your answer in, it must be in that time frame. So when you do your data, which we're going to look at in a moment, the half-life, if it's in years, will be so many years. If it's minutes, seconds, days, years, millions of years, please look for that time unit there. All you're doing here is a little bit of interpolation of your graph. So I'm going to say it starts at 1,000. I'm going to be really crude. I'm keeping it straightforward. 500. So the half-life, let's say this is of our radioactive isotope of carbon. Half-life is the time taken for the activity to fall to half of its original value. My line starts at 1,000. Half of 1,000 is 500. I'm going to interpolate my graph now with my ruler that's in my nice pencil case that you get in the exam, and your ruler. Draw a line across, so you hit the line. Stop. Go down to your x-axis. And wherever it lands on the x-axis is where you will work out the time period. So I'm going to use 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. If it was in years, the half-life would be 2 years. If it was seconds, it would be 2 seconds, and so on. Just be careful, though. There are questions where, and I'm going to extend this, where they will try and catch you out. So the axis for the y-axis may go up to, for example, 1500. Don't do half of 1500. If you notice, the line begins at 1000. So that is your initial activity, starting activity. Don't just go to the top of the y-axis, work your way downwards. You need to look for the start of the line with that one, and that will explain it. If you wanted 2 half lives, just go half again. So half of 500 is 250. Okay, go across, go down, so it'll be 3. Half of 250, half again. Just keep going and going and going and going. They could potentially give you a table of data. So they could give you the raw data this graph was produced from. It is possible. Don't let that scare you. It's exactly the same thing. So what you could end up with, you could have the time, and you could have the activity once again in becquerels. That's just a unit of measurement named after a gentleman who did some work on radiation, Henry Becquerel. If you've got 1 BQ, you've got 1 atom decaying, or 1 nucleus, if I'm being good, 1 nucleus decaying per second. So it's a rate. Okay. So we could have time, and bear with me, I'm using some numbers here, and it will all make sense in a minute. I'm not going to put all down. 366, 400. If you just tuned in a little kind of nutter now, just writing random numbers down, please bear with me, and hello. Okay, and the activity, 10,000, then 5,000, then 2,500, then 625, okay? Then 312.5. Now, if we're giving to an exam, I'm just writing it 156.25. You could be asking this to work out the half-life. So the time taken for the initial activity to fall to half of its original value. Started there, half's there, read across, 122 seconds. So it's no different to anything with a graph. It's just using table data. This bit is higher tier only now, okay? Which is the way the specification one word it is express the net decline as a ratio. That's how they will word it. And I'm going to put a big HT for higher tier. So if you are a foundation tier, you can chill out. You can nip for a wee, you can get a drink of pop and come back in a couple of minutes. You do not need this. This is higher tier only, the next bit, which is expressing the net decline as a ratio. The question could say something like, and this is brand new spec, this is brand new to the spec, so just bear that in mind. And you know, all your teachers will have been saying, well, things that are brand new to spec may crop up. We have seen some of that come on the bio and chem. You know, we don't see the papers, you know that, we've told you before. So just keep that on your radar. We'll just bring it to the front of your mind for this one. Question could say, express the net or determine the net decline as a ratio after 3 half-lives. Okay?
I really don't like that brown pen.
Oh.
Please don't use a brown pen.
And you said you don't like it. So.
You said you didn't like it. Look at this.
So decide the net decline, expect separation after 3 half-lives. The first thing we need to do is work out our initial activity. It started at 10,000. We then need to work out 3 half-lives from our table. This one here is 1 half-life. This one is 2 half-lives, so that's 1. This one is 2. Okay. And I'm just going to change that data. What I've done is this one out. Bear with me. Just change that so it works. Sorry, I'm getting overexcited when I copied them down. There you go. Don't worry about that. I've just changed the data that we use. Nothing for you to worry about. So that's 2 half-lives. Half again. That's 3 half-lives. So we now need to, I'm just going to write it down. We need to know the activity after 3 half-lives. 1, 2, 3. So that is activity after 3, which is going to be 1,250. To put it as a ratio, then all we're going to do is take those numbers. We start with our activity after 3 half-lives. We then put our initial activity, cancel it all down through the power of maths and magic, and you should get, hopefully, 1 to 8. Okay. So, quick recap, and I've said one, I'll say it again, this is higher tier. So if you're on foundation, you do not need to express it as a ratio. You may be given table data to ask half-life from, but you would not be expected to do the net decline as a ratio. So initial activity, the activity after 3 half-lives, because that's what the question wanted us to do. Work out the numbers, put them as a ratio, cancel it down, and you're sorted. Okay. Last one, really quickly, and then we're sorted. 2 words, new to this specification, irradiation, and I want to draw some pictures so you remember this one, irradiation. And I'll put it here. Contamination. Now, we'll draw some diagrams here for this one, because the bit I'm drawing this is my Twitter bird I did about an hour ago. Irradiation is when someone or something is exposed to ionizing radiation. So, for example, and I'm going to crack out some pictures. So, I'm stood here. Quiff, half a beard, I'm trying. And Miss Ness is firing half particles at me. Okay, that's radiation. So I'm being exposed to ionizing radiation. In this example, I am not radioactive. Okay. The other type, or the other danger associated with this, is contamination, where we've got the unwanted presence of radioactive nuclei. Now, I'm going to go back to my example with this one, but I can't use Mr. Ness, I can use myself. And I'm going to, in fact, actually, no, you may have heard years ago of a Russian spy called Alexander Litvinenko. Okay, he was actually contaminated because, in simple terms, he physically had the radioactive nuclei in or on his body. He was actually poisoned. He swallowed some ionized, something with containing ionizing radiation, which was polonium. So a little bit of a difference. He's got a big head. I don't know why he's got a big head. So it could be he is swallowing some spoon on there, alpha particles. I can't draw a couple of tests too intense, Mr. Cattrall. So when you've got contamination, it is the unwanted presence of radioactive nuclei. So in our case, if you're irradiated, it's like being stood next to a source decaying and emitting alpha, beta, or gamma, and you're exposed to the alpha, beta, or gamma radiation. If you're contaminated, you've actually got the radioactive nuclei on you or in your body. So if, for example, you went to Chernobyl and you rolled about in the power plant, you went and starfished on the floor, made some radiation angels, you will be contaminated because you have got the unwanted presence of those radioactive nuclei physically in your body. If you just stand near to it, you will be irradiated. The biggest one here is you are now radioactive. Bit overkill in the underlining with that one. There are questions that will ask you to compare irradiation and contamination and the dangers associated. The biggest one is you're not radioactive there. This one you are radioactive. Okay, that concludes our Trilogy physics revision. So we have covered tonight Spec 1, which is energy, Spec 2, which is the electricity topic, Spec 3 for particles, and then Spec 4, atomic structure and radiation. If you have got any questions, Trilogy people, please continue to send them through. We're going to take a break in a moment. Mr. Cattrall is going to get set up and do some separate revision. That is for set 1 only for Horizon students. You may be in other sets at other schools and you may be doing separate. That's fine. But for Horizon students, it is only set 1 people, which is only people in year 11 who have Mr. Cattrall for physics. Anybody else, if you've got the pleasure of me, or you've got the pleasure of Mr. Roscoe, or you're in E4A or out like that, please, please, please switch off. We're now done. We will load the video after this, and then you can pause, rewind, replay as you go through. We'll take a quick break. Trilogy people switch off. Separate people, nips at loo, get a cup of tea, get yourself comfy, flush your cushions up.
Okay, welcome back, boys and girls. We're going to do a quick recap of some of the key things that are physics only. So we're going to go all the way to Spec 2, which is electricity. And one of the things that you need to do is to understand what static electricity is. So I've got a quick question here. What is static electricity and how it's formed? Well, static electricity, the key word there is that it's static. It's formed when you have friction between two insulating materials, okay? And because they're insulating materials, okay, the charge cannot flow, okay? I know I'm using the brown pen that Miss Nerissa doesn't like, but I quite like it. It's showing up quite nice, okay? So static electricity is when you have friction between two insulating materials and the charge cannot flow. So it builds upon things. Now, one of the things that we need to remember is that when we're creating static electricity, we have the movement of electrons. Okay, they're the only part of the atom that can actually move. So we actually get one of the materials becomes positively charged and one of them becomes negatively charged. So that means that they are ions. Now, there are two materials that you need to understand how they become charged, okay? And they are polythene and they are acetate, okay? So I've done a pre-prepared diagram here for polythene. So I've got a polythene rod, and you might have done this experiment where you rub the rod with a cloth, okay? And as you're rubbing the rod, okay, electrons actually move from the cloth onto the rod. And if electrons are moving from the cloth onto the rod is gaining electrons, and therefore it's going to become negatively charged. Whereas when you've got an acetate rod,
so we just, it's a little bit out of focus, so we're just going to put a piece of card underneath it to try and neaten it up for you, Year 11.
Okay. That was a bit difficult trying to read Mrs. handwriting. Okay. Now, if we take an acetate rod and we rub our acetate rod with a cloth, what we actually get here is when we're rubbing the rod, the electrons move from the rod onto the cloth, Okay. All right. Sorry. Yeah. Move from the rod onto the cloth. So the cloth gains lots and lots of electrons, and the rod actually becomes positively charged. So just remember, when you rub a polythene rod, it becomes negatively charged. When you rub an acetate rod, it becomes positively charged. Now, what we need to actually remember then is that like charges, okay, so that's the same. So two positives or two negatives, they actually repel each other, okay, whereas unlike charges, okay, so a plus and a minus, or a minus and a plus, they attract. So one of the things that they could actually ask you in the exam, they could say, okay, I've got two rods here. So there's rod one, okay, and rod one is positive, okay, and it's brought close to rod two, and my second rod is negative. Can you explain what happens? Well, because they're opposite charges, or unlike, they will attract each other, they will become close together. If I had a rod that was positive, okay, two positive rods, they would repel each other and so forth, okay? So again, there's a key thing there, and it's what is an electric field, okay? Now, an electric field represents the one of the things I could ask you to do tomorrow, or you could be asked in the exam, is to actually say, okay, this object is positively charged, and you draw some electric field lines on it to represent that. Now, when they ask you that, you need to have at least 4 lines, okay? And those 4 lines have to be connected in a specific way. They must always be at right angles to the object. So I'm putting 4 lines on here. I'm going to put 4 lines on this one as well, okay? And if it's actually a positive charge, we have arrows going away from the object, okay? If it's a negative charge, we have arrows going towards the object. Very, very important there. So remember, charge flows from positive to negative. So positive away, negative towards, okay? Now, the other thing that I could ask you to do is to represent the size of the charge. And all that basically means is the bigger the charge, the closer the field lines are together. So with this one, you can actually see I've put extra field lines on. They're closer together. There's more of them. They're all at 90 degrees to the object. So this has got a larger electric field. Okay. So again, it's worth just remembering, all right, those key points. Now, we just need to remember that if we had, for example, in this case, a positive charged object and a negatively charged object, they are going to move together. They're going to move together. They're going to come together. And that's because they're oppositely charged. And that is an electrostatic force. And it's a non-contact force. Okay, they're not physically touching, but the opposite charges, the plus and the minus, okay, are going to cause them to come together. All right, so that's sort of like the basics around electric fields. The last little thing, and it's a bit of an outside chance they might ask you this, is they might ask you about lightning. How does lightning actually form? Now, lightning forms because the particles in the air move up and down rapidly, rubbing against each other and become charged. Now, air is an insulator. However, when air is ionized, that allows the electric charge to flow. And that's because you get the creation of potential difference, which allows current to flow, and therefore we get sparking. Okay. Now, if we actually go to the spec on atomic structure and radioactivity, we need to know about fission and fusion. And these are both nuclear. So we need to know about nuclear fission and fusion. So when we're talking about fission, we're talking about the splitting of nuclei. And when we're talking about fusion, we're talking about joining nuclei. Now, fusion's the easiest thing because fusion only ever happens in a sun or a star, and it's when hydrogen combines to form helium, okay? And on this spec, that's about as much as you need to know. When you come to later on to spec 8, you need to know a little bit more detail. Whereas with nuclear fission, we need to know how that actually happens. And how that happens, simple diagram, we have a neutron, I'm going to put there an N for neutron, which is fired at an unstable large nuclei. Now, you need to remember that these are potentially going to be uranium or plutonium. Now, as a neutron combines with the nucleus, it makes it even more unstable. It splits into 2 smaller nuclei, okay? I've drawn those quickly. So there's 2 smaller nuclei, so there's 2 smaller nuclei, okay, and they're krypton or barium. As they actually split, they release a large amount of energy, okay? All right, so in that process of splitting, they release a large amount of energy, and they also release 3, and this is important, 3 more neutrons. Now, what's really important is that those neutrons can then go on and hit 3 more uranium nuclei, which again, they split. Okay, and we get another 3 neutrons, another 3 neutrons, and that's what we call a chain reaction. Okay, so again, all we need to remember here is what fission and fusion is. Now, this is often a really nice 4 or 6 mark question to really describe or explain what's actually happening. So let's just remember a slow moving neutron is fired at a large unstable radioisotope, either uranium or plutonium. This makes it even more unstable. It splits to form 2 smaller nuclei, at the same time releasing a large amount of energy and 3 more neutrons. Those neutrons can then go on and continue the reaction by hitting more uranium nuclei, which then cause them to split and therefore produce more neutrons, and it becomes a chain reaction. Okay, so that's the essential extra bit that's there in the radioactivity. Now, I'm just going to finish off by looking at pressure, because I know that you're all probably feeling a little bit under pressure here. Now, we know that any container that's got a gas in it, the particles will be moving and they will be hitting the container walls. Now, when we're talking about pressure, what we're actually saying is the number of collisions with that wall is what causes the pressure. But however, when a particle hits the wall, the force that is transferred to the wall is at 90 degrees, okay? So this is our definition. So when a particle collides with the wall of its container, okay, it bounces off, but the force applied to the wall is at 90 degrees to the collision. So that's our little diagram here. Now, let's just think about this. If I've got, and let's think about Mr. Schuller's diagram about gas particles. Gas particles move around randomly, bouncing off things in all different directions. So when they're hitting those walls, okay, they're causing pressure. Now, they're moving with kinetic energy, okay? Now, if I heat up the system, so I put some thermal energy in, this is part of our energy transfers. If I put thermal energy in, okay, the kinetic energy is going to increase. And that means that those particles are going to be moving around faster and they're going to collide with the walls, and this is very important, more often. If they collide with the walls more often, the pressure goes up, okay? Now, if I have our container, okay, and I put a plunger in it, and I push that plunger down, I'm going to be reducing the space. So if I reduce the space, the particles are going to collide with the walls more often because there's less space for them to move around in. And therefore, if I lower the volume, I increase the pressure. Okay, so really quite simple. The hard bit is to get round is when we have work done on a gas. Okay, so let's pretend Mr. Schuller's gone out to his car. So here's Mr. Schuller's nice new car, make a really fancy one. Okay, look at that. Okay, it's got wheels, and it's the wheels that we're interested in. So there's Mr. Schuller. He's finished now, and he's going home. Okay, but he's a little bit unhappy because as he's driving off, he notices that one of his wheels is not pumped up. Okay, it's a bit flat. So out pops Mr. Schuller. Okay, there he is. Okay, he's got his foot pump. Okay, and he's got his big foot on there. Okay, and it's connected to his tire, and he's going up and down, pump, 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 pump. It's really hard work, but his tire starts to inflate. Now, Mr. Schuller will all agree, okay, he's a bit unhappy because he's having to do some work. Okay, so he's doing some work on the foot pump. All right, he's forcing that gas into that tire. Okay, and as he's pumping that tire and forcing the gas in, okay, the pressure is going up, but also the temperature is going up. Okay, because as you do work, because work done is the transfer as an energy transfer due to a force, so we're forcing that in there, the particles now got more kinetic energy. And that means that they're going to be moving around a lot faster, and they're going to be colliding more and more and more. So we need to just remember that when we're actually doing work on a gas, we are using a force to squeeze most of them into a space, and that causes the temperature to actually increase. And they're essentially the key extra parts for our separate science. So remember, static electricity, a big one. Remember, when you rub your polythene rod, it goes positive because you lose, it's negative because you're gaining electrons. When you actually rub your acetate rod with your cloth, okay, it becomes positive because it loses electrons. Remember that charge and how we represent charge, and then just think about fission, fusion, and gas pressure. And with that, ladies and gentlemen, thank you very much and have a good evening. We will see you tomorrow. And just remember, and this is Miss Naressi now, she's joining Mr. Schuller, and she's happy because it's home time.
Very true. So thank you very much for watching Year 11. Don't forget, Mr. Schuller says he'll be available from 6:30 in the morning, rather him than me. But you also have your physics booster in your normal physics rooms at 11:45 a.m. Thank you. Good night.
Good night.